All right, hey guys. Hey, I just wanted to go through the lab itself. I know this is kind of a confusing lab to go through, and especially when we're not there and I can't really help you through the entire process. So I wanted to walk through it of how I have it set up, um, including the analysis, so you can kind of walk along with how I'm working through things. Okay. So the first thing is that I found different charges, right, and we multiplied them together. So charge one and charge two. Um, Multiplied them together. So this column here is my product of all the charges. You can see this is equal to A2 times B2, and I just have that down. And then this is the force that was a result of that product. And what we have is we have that equation here that was graphed. We get an equation of a line is y equals 2.17 times 10 to the 13 x plus 1.22. Right? It matches the data perfectly with an r squared value of 1, which really it's a simulation show, so it should match it very well. Now, let's go to the distance ones. Sorry. And I don't know why I have these marked as something different, so I'm just going to change those real quick, and then you'll notice my y-axis is not labeled correctly, but so I apologize for that, but it should be force. But here's what we have, right? So we have our distances from the simulation, and then we have the electrostatic force that was present based on the distances. And we should get a graph that looks like this. Now, this is an inverse relationship, okay? And what that means is that as this x value is getting bigger, the y value is getting smaller, okay? So that produces a 1 over relationship, okay? So y equals or is proportional to 1 over x, all right? So how do we try to linearize that? And we'll go through this more as we come to this more often in the class. But so the first way I can try to linearize that is just by doing 1 over x. So taking my x values and doing 1 over them, okay? And when I do that, these are my new x values. Okay, so these are my new x values. My electric force values don't change, and I get a graph that looks like this. Now, again, this, because we're limited in the data that we took, this looks somewhat linear. It actually has an r squared value of 0.986, which is pretty good, but it's actually a parabola, right? So it actually has a curve to it that we just can't see it based on the limited data that we actually have, okay? So with the lab, then what we're going to do is 1 over r squared. It's called the inverse square law, and that's present in a number of different force equations that we'll look at. But this is what I get. Okay, so again, these are my distance values that I squared them and then did 1 over that squared value. And when I compare that with the electric forces, then we get this equation here. And you can see my r squared value actually went up to 0.994, so that's a really good comparison. And so what I'm going to do is I'm going to take this graph and then the other graph, and I'm going to superimpose or copy them into the lab. I made a copy so you can kind of follow along, and I'm going to work through the analysis. Okay, so I did the analysis, and so you guys can kind of see how I would work through this. So the first part says rewrite the variable associated with each graph's trend line. Okay, so the trend line is linear, so it should start out for both of them as y equals mx plus b. Okay, I'm going to move this over here so it's a little bit easier. Y equals mx plus b, y equals mx plus b. If I had to rewrite that, the y value on this graph here is force. My x value is the product of charge 1 and charge 2, so q1 times q2. We dropped b because it was really close to 0 and insignificant, so it's not really worth keeping around. Now on this one, again, this was force. It's labeled wrong, and I apologize. So y equals force. X value, then, it's the inverse square of the distance, right? 1 over r squared. So that is x, 1 over r squared. Okay, so that's how I rewrite my equation of my line with the variables that I'm actually using in each graph. Now, the next says the slope is not your value for Coulomb's constant, right? Our slope is actually a combination of Coulomb's constant along with the constants you maintain in the lab. So for this graph here, we kept our constant. We kept the distance constant. For this graph here, we kept the charges constant, right? So basically the slope of this graph is going to equal Coulomb's constant, right, multiplied by 1 over r squared. Really, we can have this as an r. Okay? This x value from this graph is in the slope of this graph. And the opposite for this one. Q1 times Q2 is in the slope of this graph. So my slope is this unknown constant times charge 1 times charge 2. So your goal then is to determine Kc, Coulomb's constant. All right, so to do that, I'm just going to manipulate that equation and figure out that over here, Kc is equal to the slope times r squared. And over here, Kc, the Coulomb's constant, is equal to the slope divided by the product of Q1 times Q2. Okay, so from your graph, you then should be able to take your slope values along with the constants that used in your lab and basically just plug them into that equation. Okay, so that's what I showed here. And from that, I should get two different Coulomb's constants, 8.68 times 10 to the 9th and 9.3 times 10 to the 9th, right? A little different, and that's okay, but they're actually pretty close. The next part is I have you guys check with a percent difference from the actual accepted value, right? The accepted value is 8.987551 times 10 to the 9th. You do not have to use that value. I'll explain here in a second. And so I find my percent difference of actual minus experimental divided by actual, and I got 3.3% difference and 3.5% difference. Okay, so pretty good. And the last thing is I ask you to determine the units for this constant. All right, so if I had to know what units I'm plugging in, how do I actually figure that out? So here's this equation down here. Basically, I combined these two equations, right? I combined these two equations, right? Q1 times Q2 over r squared. And those two multiplied by some Coulomb's constant is going to give me the force. Right, so here are my units. Newtons for force equals the Coulomb's constants units times Coulombs divided by meters squared. Coulombs is how we measure charge, and meters squared is how we're going to measure the distance, or meters, and then we're going to square it. So if I have that, that becomes Coulomb squared on top. Coulombs times Coulombs is Coulomb squared. I'm then going to do a little bit of algebra and solve for Coulomb's constant. So I'm going to multiply by m squared. I'm going to divide by Coulomb squared, and I get the units for Coulomb's constant is newtons meter squared over Coulomb squared. Okay, and that makes sense because the equation itself has Coulomb squared on the top and meter squared on the bottom, so those have to cancel out. So I need Coulomb squared on the top to cancel out with this Coulomb squared on the bottom, and I need meter squared on the bottom to cancel out with this meter squared on the top. And once I do that, all that I have left are newtons, and that's good because newtons are how we measure forces. That is a rundown of the lab analysis. I know it, again, is tough in a digital environment, but hopefully you can follow along with that as you're working through your lab.